So in this lesson, we're going to talk about the net force, and the learning target is to be able to calculate the net force on an object and describe how it affects the object's motion. So if we look at finding the net force, this is going to not be too bad. We should be able to make sense of it here. So if we're looking at, I just draw this X out because it doesn't really matter if it's there or not. So when we're finding the net force, there's two rules that we need to apply here. Is if two forces are pushing in the same direction, they are going to add together. It's like if I was trying to push a refrigerator or something like that, and I maybe couldn't do it by myself with my long body, and I started pushing on this thing. The best thing that I could do is to get a buddy to help me, and he could push from way back here and push, and our forces of both pushing in the same direction are going to add together, and this refrigerator is going to move in that direction. Now, if my buddy was mean and instead of being helpful, came over and stood on the other side of this refrigerator and pushed the other way, this way, our forces are going to cancel out from each other, and this thing isn't going to go anywhere. And so if forces are acting in opposite direction, where they are acting, one's acting right, one's acting left, we are going to subtract those forces from each other. And if they're moving in the same direction, like I said the first time, we're going to add those forces together. And those two rules are pretty much going to tell us what we're doing for finding the net force. And so if I look at this object here, I have this box and I have 6 newtons up and 6 newtons down. I have probably a normal force right here, and I have the force of gravity acting down. And now another part of this net force is that we need to remember that only our up and down forces are going to interact with each other. They do not interact with our side to side forces, our left and rights. And so in this case, if we were trying to figure out what our net force would be for the up down direction, we would take 6 minus 6, and we would get an up down force of 0 newtons in the vertical direction. So I'm not going to draw anything vertically on this box. Now, if I'm looking at my right and left forces, those two are different from each other, and those two are going to interact with each other, but they're not going to interact with the vertical forces. And so if I look at my leftward force, I have 3 newtons acting to the left, and I have 20 newtons acting to the right. And so how I would find my net force here is I would take 20 newtons minus 3 newtons, and I get 17 newtons. And that's going to be my net force. And I'm going to draw that in the direction of the bigger force, this one right here. Another way we can think about this is that we have 20 newtons acting in the positive direction, in the right direction, and we have 3 newtons acting in the negative direction. Right? And so we have 20 minus 3 equals 17 newtons, and we're left with a positive 17, which acts in the rightward direction. So we would say that our net force, F net, equals 17 newtons acting to the right. And so this is how we find the net force. Remember to keep them in the vertical, separate from the horizontal forces in this one. And so if we have this problem right here, a textbook is sliding across the desk to the right, the forces acting on it are shown right below here. What is the net force? Well, the way that we're going to do this is we're going to draw a new force diagram. And remember, I look at my vertical forces separately. I have 3 newtons minus 3, which equals 0. So I'm not going to draw any forces in the up-down direction, my vertical. And then I look at my horizontal forces, and I have just my 5 newtons acting to the left. And so I don't have anything on the right side to balance that out. And so I am going to have a net force of 5 newtons acting to the left. And so if we look back at the problem, that's the first one, is the net force is 5 newtons acting to the left. And how will the book's motion change? Well, if this object is moving to the right and we're pushing back on it to the left with friction, this object is going to slow down. Because remember, if we have an unbalanced force, we have a net force. And if we have an unbalanced force, there's going to be an acceleration happening. In this case, we're going to accelerate to the left. If we're moving to the right and we're accelerating to the left, we are slowing down. And you can think about it, what's pushing back against that object, and friction is pushing back against it, so it's going to slow it down here. And so our net force would be 5 newtons, and we would be slowing down in this situation. So look at this problem here. A box is pulled to the left with a force of 10 newtons across a frictionless surface. The force of gravity on the box is 200 newtons. What is the net force? So we're going to go back and we're going to draw our overall force diagram. We're going to just see what are all the forces acting on this thing. And so we go back through our questions. Is gravity acting on this object? Well, yes, it's on Earth, and the problem says that gravity is acting on it. So we know that our gravity, F grav, equals 200 newtons. And we know that it's acting, or that it's held up by a surface. It's held up by something. Well, it's moving across a surface. And so I would know that there is a normal force. Okay, and I know that this object isn't falling down. And I know that it's being held up by the surface, and so I know that the up and down, our vertical forces, are balanced in this situation. Otherwise, it'd be accelerating either upwards or downwards. And so since I know that it's being held up and balanced, I can write that my normal force is 200 newtons. Right? So that takes care of my vertical direction here. I see also is the box being is any force being applied onto the box. It's moving to the left with a force of 10 newtons. Right. So my force applied is 10 newtons to the left. And I look at the problem and it says, and I ask myself, is it sliding? Is it rolling? And I say, well, it's sliding across the table, but the problem tells me to go a frictionless surface. And so I am not going to add friction into my force diagram. And so this would be the overall force diagram here. But now we go back and we look at, well, what's our net force? Right, so I look at my vertical, my up, down. I already said that they're balanced. I have 200 newtons acting downward, 200 newtons acting downward. And so I'm not going to draw anything in the vertical direction on my force diagram. But then I look at the right-left forces, and I see that I have 10 newtons acting to the left, and I have nothing acting to the right, and so I know that I am left with a net force of 10 newtons acting to the left. And so that would be my answer to problem number 1. And then how does the box's motion change? Well, if we have an unbalanced force, remember we're getting acceleration, this thing is being pulled to the left, and so since a force is acting in the direction that it's moving, this object is going to accelerate or speed up left. That's how the net force would affect its motion. So the same box is pulled to the right with a force of 40 newtons across a rough surface, which applies a friction force of 10 newtons acting on the box. What is the net force? So let's go through this one. We've got our box, same box, and I remember from the last one, it is a force of gravity is 200 newtons. I know that it's still being held up by a table, so I know that the normal force is also 200 newtons. It's being pulled to the right with a force of 40 newtons. So F applied equals 40 newtons. And I know that it's sliding across a table and it has a friction force of 11 newtons. Well, it's being pulled to the right now. And so since it's moving right and friction acts against the direction that it's moving, I'm just going to write F for friction. That has a force of 11.0 newtons. And so what is my net force? Well, I'm going to draw that out in the box here. And so I look at my vertical forces. I see that I have 200 and 200. Those are equal to each other, and then they're in opposite directions. So those are balanced. So I'm not drawing a vertical force on my net force diagram. All right, well, now I look at my left-right forces, my horizontals, and I see that I have a force of 11 acting to the left, and I have a force of 40 acting to the right. And so what I do here is I take, and I just always take the bigger one and subtract the smaller one, and then remember which way that it's going, whichever way is bigger. And I see 40 minus 11 equals 29 newtons. And so I know that my net force is going to be 29 newtons. And I look at my problem and I see, okay, well, my bigger force is over here on the right side. That's my 40. And so that's the direction that's going to have my net force. Some people would say that you should keep them positive and negative. You can also do that. You can see that force acting to the left is negative force, so negative 11 plus positive force to the right of 40 is 29. Or you can just remember that 40 was my bigger one, so that my net force is going to be to the right. For our purposes, that will work fine. So my net force here is a force of 29 newtons. And if this object was at rest, we can think about how this would. Well, it would accelerate to the right in this situation if it was starting at rest. If it was already moving to the left, like in our last problem, well, what's going to happen to its motion? Well, its motion is going to start to slow down. It's going to decelerate because it has a force acting to the right while it is moving left. And so that's what would happen to it. If it was already moving to the right, it would also accelerate to the right. So that's how we take our net forces and we figure out how the object's motion is changing. We can take all of the different forces acting on an object, figure out what the net force is, and then decide how the object's motion is going to change.